Question 2, Part A, Figure 2.1 shows the covalent bonds and lone pairs of electrons in the molecule of sulfur dichloride. Then Roman 1, use valence shell electron pair repulsion theory to predict the shape of a molecule of sulfur dichloride. Now, we have the bond pairs here, but we have lone pairs on sulfur. Now, in valence shell electron pair repulsion theory, lone pair repulsion. So there's a lone pair and then a lone pair. So the repulsion there is greater than the lone pair bond pair. Okay, so this is a lone pair and then the bond pair here. So the repulsion in between these two is less than the repulsion between lone pair and the lone pair. You see that? And then in turn, we also have bond pair and then bond pair. So this one will also be greater than the repulsion between bond pairs. Okay, so bond pair, bond pair. Now, so by doing so, because of this kind of repulsion, you are going to have sulfur here. You have the lone pair here, another one here. Okay, then these ones will be forced to bend. So there is a repulsion in between these two, which is so strong. Now, the bonds that are here, there is also going to be a repulsion here. There is also going to be a repulsion here and then here. But since the repulsion here is stronger than the repulsion here, and in turn greater than the repulsion here, so this is the weakest here. So these bonds here will be forced to bend. You see that? So we can have something like this. So this one will bend, and also here. Then you have this and that. So the angle in here has to be, first of all, we take these ones as, let's say, 4 bonds. Okay, so we have a lone pair and a lone pair. If we begin with 4 bonds, you are going to have, let's say, let me begin with, maybe when these ones are 4, all of them are bond angles. Okay, now this is tetrahedral, so this angle is 109.4, even these other ones. Okay, 109.5. Okay, 109.5, 109, or 109 to 110. Okay, then what else? We are also going to have the next one. I remove this one, the lone pair, the bond pair, and then I put a lone pair. So when I put a lone pair here, and remember, lone pair bond pair repulsion is greater than bond pair repulsion. So this one is going to put another stress here onto these bonds. So the angle, which was 109.5, is now going to be reduced. Okay, then it will come to less than 109, and it will come to around 107. Now this is what we call trigonopyramidal, like in ammonia. Okay, like in ammonia, where there is a lone pair here, then hydrogen, hydrogen, hydrogen. So this one will be like 107. Now, if I remove another bond pair and then I replace it with a lone pair, okay, there is again another stress that is put onto these bonds. So this angle has to reduce again. So it has to be below the angle here. It has to be below 100 and what? 107. So we can have it from maybe 104 to 105. Okay, that is that. So I can put it on maybe 104.5. In between, it is from 104 to 105. Anywhere in between there, you get the answer. Okay, now they are saying use valence shell electron pair repulsion theory to predict the shape. Of course, the shape, this one cannot be linear. They give it to you here as if it is linear, but after understanding the valence shell electron pair repulsion theory, then you cannot have this one as linear. We shall instead put what? Non-linear. You can say non-linear, you can say V-shape. This is actually the same as that of water, same shape with that of water. Okay. Then predict the bond angle in the molecule. We have seen this one is 104.5 degrees. Then part B, sulfur dichloride is a red liquid that reacts with water. So when it reacts with water, we can see sulfurous acid here. Of course, this one is colorless. And then HCl is also colorless, but then we see sulfur here, which is a solid. It's a yellow solid. That means there is going to be change in the color. So from the red liquid, which turns colorless, because this one is colorless and this, but then there is also a yellow coloration, a yellow solid in there. So Roman 1, they are saying describe two observations. Those are actually the ones I've just said. Okay, two observations other than temperature change that are made when an excess of water is added to sulfur dichloride. So we can say the red liquid, or we can say red solution. So red liquid turns colorless. That is one. Then number two, it is about sulfur, which is a yellow solid. So we can say yellow solid appears. Simple as that. Then Roman 2, when sulfur dichloride reacts with water, the sulfur dichloride is broken down and a disproportionation reaction occurs. Remember, for a disproportionation reaction, we are looking at that one species which is both oxidized and reduced. State the oxidation numbers of sulfur in sulfur dichloride and sulfurous acid. Okay. Let us look at this one here. Maybe the oxidation state is N, then plus. We have chlorine. The oxidation state is, of course, -1, but there are two of them. Then we are equating to 0 because this one has no charge. So that means our N here is going to be equal to +2. So we shall put a +2 here. And then when it comes to this, the oxidation state of hydrogen is a 1, not so. So we have two of them, so that will be 2. Then plus the one of sulfur, I don't know it. Okay. And then this one here, oxygen, the oxidation state is a -2, but there are 3 of them. Then you equate to 0. So this is -6, then +2, that will be -4. Then when it crosses the equal signs, then it becomes a +4. So that means the oxidation state in here is a +4. Now we can see that if the oxidation state of sulfur in here is a +2, then you come to this one here, in sulfurous acid, it's a +4. So there is increase in oxidation state. So this one is going to be oxidation. See that? Then we have sulfur here. The oxidation state is a 0. You see that? Oxidation state of any element is a 0. So now moving from +2 to the 0, that is reduction in the oxidation state. So that one is reduction. So sulfur in here is both oxidized and reduced. That is why it is a disproportionation reaction. Then Roman 2, state the general name to describe the type of reaction that occurs when a substance is broken down by water. Of course, that is what we call hydrolysis. Hydrolysis is a type of reaction where a compound is broken down by application of water.